In this paper, we introduce a universal and hierarchical shell representation for discrete data, named inverse farthest point sampling IFPS. The motivation of this study is how to construct shell for discrete points in an efficient way. Discrete points may come from mesh, 3D sensors, visual structure from motion methods, or learned centers of 3D Gaussian splatting. The shell is defined as a certain 3D representation bounding surface. The shell's role is focusing on interesting areas in collision detection. Our solution to shell is inverse farthest point sampling IFPS, which results in the intersection of multiple unions of uniform spheres. It has several unique advantages. For example, our IFPS shell representation is universal, as the centers of bounding volumes are the input points themselves. Radii of bounding volumes are derived from FPS. Meanwhile, the IFPS shell is hierarchical. Both of implicit tree and explicit Q-way tree can be constructed without heuristic spatial partitioning. Beyond two-dimensional and three-dimensional, IFPS can be seamlessly extended to discrete data in any dimension, with spheres naturally generalizing to hyperspheres. In IFPS process, a local shell is obtained in each iteration, inversely processing one new FPS point. Each local shell is a union of uniform spheres. If all FPS points are used to progressively constrain the shell, the intersection of all unions of spheres will form the implicit global shell. If some certain iterations, for example, multiples of 8 are used to constrain the shell, the intersection of these corresponding unions of spheres will form an 8-way global shell. Vanilla global shell corresponds to an implicit tree, in which each father node has a son with the same center. 8-way explicit tree further improves the efficiency of tree traversal. The multi-resolution shells of the aircraft mesh and the shells of other models constructed from 4096 FPS points are shown here. For the implicit IFPS shell, we propose a fast algorithm to test whether a given point is inside the shell. Each iteration only involves one distance calculation and 2 if judgments. The first application of our IFPS shell is performing collision detection with CPU. The scenario consists of a static table and a teapot undergoing self-rotation. The teapot falls onto the table and bounces back. The second application of our IFPS shell is enhancing collision detection within 3DGS. We designed 3 distinct scenarios where IFPS plays a crucial role. The main configurations are listed here. The first scenario is snowing in a 3D GS scene. The snowfall is simulated with thousands of tiny spheres descending onto a static scene reconstructed via 3D GS. The centers of the scene's 3D Gaussian primitives are organized using the 8-way tree of IFPS. The coarse collision is detected when a snowflake sphere comes into contact with the center of the static scene's 3D GS primitives. The second scenario extends the first by considering collisions among multiple bouncing spheres, as well as between these spheres and 5 invisible walls bounding the 3D GS scene. In this scenario, the 3D GS represented hot dog moves randomly within the scene. The Gaussian primitives of the moving hot dog are organized by a 2-layer sphere tree. Thanks for watching.